On September 16, 2023, earthquake sensors worldwide detected an unusual vibration. Unlike a typical seismic event, this was a deep, continuous rumble, more like the tone of a tuning fork than the chaotic patterns of an earthquake. Even more perplexing, the signal persisted for 9 days. Scientists were left puzzled, unsure of what they were witnessing. Determined to uncover the source, a global team of researchers from 15 countries collaborated to analyze the data. By examining the precise times the tremors reached various monitoring stations, they estimated the origin of the disturbance. Their calculations pointed to a location in East Greenland. A crucial breakthrough came when researchers discovered an enormous tsunami recorded in the same region on the day the signal began. Measuring 4 times the height of Niagara Falls, it was the most significant wave documented since 1980. Given the timing, it was clear this event was connected to the seismic anomaly. However, the origin of the massive wave remained unknown. To solve this mystery, scientists turned to satellite imagery and seismic records. Their investigation revealed that a colossal section of a mountainside had collapsed more than a kilometer above sea level. As it plummeted, it fractured a glacier, sending 25 million cubic meters of rock and ice, enough to fill 10,000 Olympic swimming pools, into a fjord below. This wasn't an ordinary landslide. Several factors intensified its impact: the added debris from the shattered glacier, the steep, icy terrain providing minimal resistance, and a narrow channel that funneled the force into a concentrated area. By the time the material crashed into the water, the impact was immense, generating an enormous tsunami. With this sequence of events established, one question remained: how did a landslide lasting mere minutes generate a seismic signal that endured for 9 days? To gain deeper insight, scientists developed a high-precision simulation of the event. However, such a complex project required significant funding. And speaking of funding, let's take a moment to acknowledge our sponsor. Through advanced modeling, researchers uncovered an unexpected phenomenon. Instead of dispersing as tsunamis typically do, the wave became trapped within the fjord, continuously rebounding off its walls. This process, known as a seiche, occurs when water oscillates within a partially enclosed basin, much like the back-and-forth movement of water in a bathtub. Seiches can persist for extended periods, gradually losing energy over time. In their simulation, the trapped wave oscillated every 87 seconds, a cycle strikingly similar to the pattern recorded by global seismic monitors. To validate their findings, scientists compared the modeled data with real-world observations. The results aligned: the wave's motion corresponded with seismic readings, minor fluctuations matched tidal variations, and the signal's gradual decline mirrored the expected dissipation of the seiche. With all evidence pointing to the same conclusion, the mystery was finally solved. A tsunami trapped within a Greenland fjord had sent tremors across the entire planet for over a week. However, the implications of this discovery extended beyond a fascinating scientific anomaly. This catastrophic event was not an isolated occurrence but the culmination of a long-developing process. Climate change played a direct role. The glacier, which had been thinning for decades, had weakened to the point where it could no longer support the mountain's weight. When the collapse occurred, it triggered a chain reaction leading to the massive wave and the prolonged seismic disturbance. This unprecedented event serves as a stark reminder that Earth's natural systems are undergoing rapid and unpredictable changes. As our understanding of these phenomena deepens, it becomes increasingly important to recognize and respond to the signals our planet is sending us.